So it's a pleasure to have Petr Siegl from the Technical University of Graz today. Petr did his PhD jointly between Prague and Paris, right? And then he was a postdoc in Lisbon and in Bern, and that's where we met. And then after that he was in Belfast, and now he's in Graz. And Petr is a specialist in spectral theory, especially in spectral theory of non-self-adjoint operators, and he will tell us today about advances in spectral theory of non-self-adjoint operators. Please, Petr.
Thank you, Janko. Just start this. So it's really nice to be again in the UK for a while. In this talk, I would like to do first more general introduction to non-self-adjoint spectral theory and aspects of that, what is different comparing to maybe more standard self-adjoint case. And then I would like to move to one specific topic within, which is based on the works of Boris Mitagian from Ohio State University, and I listed a few references, including the newest preprint where we made some progress. And in general, what this is about is the properties of eigenfunctions of certain differential operators. I will get to that a bit later. So there will be two parts of the talk. First, more general, quite general introduction, and then something more specific which relates to my work. So let me start with a summary of what we actually know about self-adjoint operators. So for me, I will be in separable Hilbert space, mostly L2. And the example for the self-adjoint part, which one can have in mind, is simply the self-adjoint harmonic oscillator, where we know everything. Okay, but what do we know in general about self-adjoint operators? So we know the spectrum is non-empty, it is real, residual spectrum is empty, spectrum is purely discrete if and only if the resolvent is compact. In case the operator is semi-bounded, we have nice variation characterization of eigenvalues. And what will be important for me later, in this case of compact resolvent, eigenvectors form an orthonormal basis. So everything follows from self-adjointness. And one can go further. We have spectral decomposition, functional calculus. By that, we can construct functions of the operator, so in particular semigroup or group, and its norm is related to the spectrum of the operator. So everything is known. In this way, we know that we can solve Schrödinger equation, time-dependent Schrödinger equation immediately. We also know what is behavior of the norm of the resolvent. It is simply equal to the 1 over distance of the spectral parameter to the spectrum. So the behavior of the resolvent norm is equivalent to know where the spectrum is. So this is what I would like to stress here. And this has a lot of consequences, like spectrum is stable with respect to small perturbations. If you perturb a little, then the spectrum moves a little. This is the final formula here. The union of all spectra of all perturbations with norm less than epsilon is epsilon neighborhood of the spectrum of the unperturbed operator. So everything is kind of nice. Now, when one goes through, let's say, mathematical physics literature, you will have many examples, which won't be mostly quantum mechanics, where you sooner or later meet non-self-adjoint operators, which are typically some effective models or maybe some technical part of the analysis. It comes usually from nonlinear problems, or if not nonlinear, there's some natural way how you can lose energy or get gains of energy. And I listed a few of the examples with few more or less random references. Maybe the classical one is the Dan-wave equation. Then problems coming from superconductivity, hydrodynamics is a great source of this type of problems, or something newer, Bloch-Torrey equation, which is old, but it's model of magnetic resonance imaging, or even quantum finance. There is something else, not quantum, math finance. Even there, you can get something like Schrödinger operator with complex potential and many more.
Now, second example is really physics. I mean, with I, Y.
Yes. So,
I mean, so they do appear in real physics of superconductivity, right?
no, wave equation also takes quadratic function, but in spectral
No,
parameter, but lambda is complex. You need to analyze actually this problem most importantly on the imaginary axis. So many things are really coming from physics. Maybe they are not of the type, they are not equivalent to Hamiltonian in Schrödinger equation, but you anyway need to study their properties to say something reasonable. So it's not just a game. Okay, now let's go back to our list of properties of abstract non-self-adjoint operators. What stays? Spectrum can be empty, and it's usually a hard problem to show that it's not empty. Of course, it does not have to be real, that we know also. For matrices, residual spectrum can be non-empty. That's not difficult to see. Compact resolvent implies purely discrete, but not the other implication. No variational formula for eigenvalues, and certainly no basis properties of eigenvectors that can be lost completely. No spectral decomposition, no functional calculus in general. Even if you can build a semigroup, its norm does not have to have any relation to the spectrum of the generator, because the norm of the resolvent is given by the spectrum and the behavior of the resolvent. And the behavior of the resolvent can be unrelated to the spectrum. For the norm of the resolvent, one inequality stays that if you approach spectrum, norm of the resolvent blows up. This stays, but not the other way. You can be far from the spectrum, but still norm of the resolvent is large, which again has consequences. For example, the spectrum of is not stable with respect to small perturbations. You perturb a little, but the spectrum moves a lot. Okay. Now, let me illustrate this by three famous examples. So on the left, I listed what would be true for self-adjoint, and then there is always some easy example, is well-known example, non-self-adjoint, that shows that even in case of differential operators, not only abstract operators in a Hilbert space, these things can happen. First one, spectrum is non-empty. On the right, we have the area operator, one dimension, linear potential. This is compact resolvent, but the spectrum is empty. So already that appears for the simplest case. Then other property of the self-adjoint operators, compact resolvent, eigenvectors form an orthonormal basis. They go to the imaginary oscillator, Davies oscillator. Resolvent is compact, spectrum is very nice explicit, eigenfunctions are very nice explicit. These are just transform Hermite functions, but they are complete, but they do not form any basis. So you lose this. Third thing, also kind of famous operator, IX-cube potential. In this case, and this is surprising, spectrum is real. So it looks like, if you just look at the spectrum, that there is nothing wrong with this operator. You put it to the time-dependent Schrödinger equation and you think, okay, this should be like self-adjoint. One should be able to solve it, meaning you should be able to, or hope to be able to construct the group or a semi-group for Schrödinger equation. And this would be absolutely okay for self-adjoint case. The norm of it would be 1. You cannot. No bounded semigroup exists, so you cannot solve for general initial data time-dependent Schrödinger equation. And this one, the last picture, is the so-called pseudo-spectrum for the last case for the cubic oscillator. So what you can see here, this is the part of complex plane. The red balls are eigenvalues, and these curves are levelized of the resolvent norm. They are decoded in color, so basically it is like this. As you move to the right, the norm of the resolvent is larger and larger. For self-adjoint operator, this would be only larger and larger epsilon neighborhoods of these red balls. But here, instead of neighborhood, you see these V-shaped regions. So they extend like that. So you can go very far from the spectrum and norm of the resolvent stays big. So this is maybe illustration of that something can go really different comparing to self-adjoint cases. Now, if you then summarize, what do we do in spectral analysis? Maybe focus on non-self-adjoint. Maybe my personal point of view of in which areas I would go are these four parts. Well, the first thing is very much analogous to the self-adjoint case. Let's say I have Schrödinger operator, and first thing I would like to do is to define it properly. So I need to find correct domain. In this case, it's not about self-adjointness, but I would like to find correct domain so that the resolvent set is non-empty. This would be analog of being self-adjoint. There are many methods for that, form methods, other things, so generalizations of flux monogram, things like that. I won't really speak about this today at all, but this is one of the big parts of spectral theory. Then maybe the most classical one is, okay, I have already good operator. I know that the spectrum is not everything. So the question is, where is the spectrum? Localization of spectrum. Now, of course, in non-self-adjoint case, I need to look into whole C and check the invertibility of lambda minus A or its Fredholmness, and so on and so on. So in a way, this is similar to self-adjoint, but in non-self-adjoint, one goes further because even in a nice case, compact resolvent, only discrete spectrum, then comes the question, what can I say about eigenvectors? In self-adjoint case, I would know they form orthogonal basis, everything is fine. Here, I don't know a priori. So are the eigenvectors complete? Can I expand arbitrary vector in eigenfunctions? And then more subtle things like decay of eigenfunctions, concentrations, weighted norms, LP norms of for differential operators of eigenfunctions. This is a huge area of interest. And maybe finally, behavior of the resolvent. So in self-adjoint case, if you know where the spectrum is, you know how the resolvent behaves. But this is no longer true in this world. So this is completely independent topic in this area, where you try to get both lower and upper bounds on the norm of the resolvent. And if you get that, then you can conclude, let's say, existence of semigroup or stability or instability of the spectrum with respect to perturbations. And what I would like to do today, I would like to concentrate mostly on this part 3, so properties of eigenvectors. So I will go now deeper into this topic, and it has a lot of relations with the behavior of the resolvent norm. I will show it. Okay. So now what I presented, there are like two extremes. I started with self-adjoint operator, where everything is known on abstract level and large amount of really nice properties is coming from abstract operator theory. On the other hand, other extreme are general non-self-adjoint operators, where basically no general statement can be given because, as I showed, whatever you like to have, you find counterexample, even if you specialize only to differential operators. But this differential operators are often not like that. They are not this extreme non-self-adjoint. They often come as kind of perturbation of something nice of self-adjoint. So let's say we have this T is equal to A plus B, A is self-adjoint and B is small. The point of what is coming is, what does it mean small then? Example one can have in mind is standard self-adjoint harmonic oscillator one dimension, and I perturb by something imaginary. For simplicity, I wrote it as an odd function, so it's odd extension of x to gamma, okay? And I want to play with gamma. Now, one would expect that if gamma is small, then this operator, well, it won't be self-adjoint, but its properties should be, I hope, are close to the self-adjoint. If gamma is big, then I expect all the pathologies that I showed there, nothing can hold in general. But now the question is, where is this transition? So what is, let's say in this example, where is the threshold for which gammas I'm still good behavior, I have everything under control, analogous properties to self-adjoint case, and beyond that, I go wilder, and it's typical non-self-adjoint behavior. Now, before I get to the answers of that, I would like to mention two examples. That one on the right, B2, so is the case of gamma equal 1, x squared plus ix, okay? And let me first comment on that. So in this case, spectrum is explicit, even eigenfunctions is discrete, real, You can find it, it's just moved spectrum of harmonic oscillator. But these eigenvalues are unstable. You have problems with the stability with respect to perturbations. Eigenfunctions, they do not form a basis. And if you try to solve time-dependent Schrödinger equation, you cannot. And there is no bounded set. Okay. The first example, B1, is something kind of different. I put I, epsilon, small but fixed. And then two delta functions also organized in a way that I get something odd. Okay. Now, in this case, spectrum is also real. For that, I want this epsilon to be able to compare these examples in this way. But the eigenvalues are stable. Eigenfunctions form some kind of basis that I will explain. One can solve the time-dependent Schrödinger equation. Okay, these two examples look completely different. One is perturbation somehow is bigger than infinity. The other one is singular. But my point here is that if you measure the strength of the perturbation in these two examples in one of the classical ways, their strength is the same. And this is the final inequality here. If you compare the quadratic form of the perturbation and the self-adjoint part, you will see that it's controlled by the same power of the quadratic form. In the second case, this is application of Hilbert inequality. In the first case, is application of trace embedding. In both cases, you can't improve. So this inequality is as good as it can be. In both cases, you get P equal 1/2. So the message after this is that trying to measure the strength of perturbation by, let's say, classical way of inequalities of this type cannot distinguish between good and bad case. It is too rough. The criterion distinguishing between B1 and B2 need to be more subtle. And this is where I would like to get eventually. Okay, so before that, let me recall a few things because I need to express it so that I can express the statements. So in separable Hilbert space, if we have a set of vectors E is complete if the span of E is dense, or equivalently orthogonal complement is just 0. And in case E is also orthonormal system, then complete orthonormal system is orthonormal basis. So it looks like that completeness is that thing that you need to get to a basis. But if the system is not orthogonal, this is more complicated than that. Next step, E is a basis if every vector has a unique expansion into the elements of E. I won't really talk about basis much. For me, the most important notion will be the so-called Ries basis, which means that E is a basis, and moreover, one has a control of Fourier coefficients, if you want. So from both sides, the sum of the Fourier coefficients can be controlled by the norm of the vector. For that, I won't really use this characterization. We typically talk about the equivalent expression. System as a Ries basis if there exists a bounded operator W with bounded inverse and an orthonormal basis such that psi n can be mapped to this orthonormal basis by W. So in this way, Ries basis is a basis that is equivalent to an orthonormal basis, and the way how you go from orthonormal basis to Ries basis is boundedly invertible map. So it is a similarity transform, if you want. In case, of course, this W is unitary, then you map orthonormal basis to orthonormal basis, but I'm not asking for unitary. It can be non-unitary, but bounded with bounded inverse. Now, for what comes later, it is more convenient to reformulate these notions in terms of projections, because then I don't have to explain how do I select the vectors. So projection is for me just P squared is equal to P, nothing more than that. No orthogonality. And system of projections is called disjoint if PJPK is delta JKPJ, so the usual thing. And this will never be an issue in what I'm going to say, because these projections will be constructed as disjoint. So this property will be somehow automatic in everything what will come. The next thing is the completeness. So now for projections, it can be formulated in this way. System of projections is complete if I take PJXY for all x in H, meaning I go here through the range of the projection PJ. product with y and I go through all projections, then necessarily this y is 0. So you can reformulate system of projections is complete if any vector can be approximated with an arbitrary accuracy by linear combinations of the elements of the range of these projections. So it is, well, the completeness is, we understand. This doesn't mean I can write the vector as convergent series. It just means I can approximate by finite linear combinations. And finally, the Riesz property of projections, I will call it the Riesz property, if they are disjoint complete, and we have this similarity transform, there exists bounded operator with bounded inverse, and disjoint complete system of orthogonal projections, such that my system PK can be mapped by the similarity transform to the system of orthogonal projections. Okay, so if we have now this terminology, the next question is, well, how can I check that the system of projections is has the Riesz property? For that, one of the classical results applies, for example, this formulation from the book of Hilbert, right? If I have system of disjoint and complete projections, then the system has the Riesz property if and only if this series converges. So for every x, this series is convergent, and this is technically really what we do in the proofs. We are really checking this this criterion. Okay, now one more remark about completeness. As I said, for orthogonal or orthonormal systems, it looks like that what is the difference between basis and just orthonormal system is the property of completeness. But actually, if you don't have orthogonality, completeness is much weaker property. And one of the ways how to see it is the following, so classical result formulation done for Schwarz, which is sufficient condition for completeness for operators with compact resolvent. So if T has compact resolvent in shuttling class P, and you build all spectral projections, the usual formula with projections, then the system is complete if there exists sufficient amount of rays in C. This amount depends on P, on the shuttling class. And the idea is that the angles between these rays need to be sufficiently large. There's a precise formula, but what it means is that the higher P is, the more rays I need in complex plane. And on these rays, normal of the resolvent should be controlled, should not explode faster than a polynomial. In this case, then the system of projections is complete. Now, if you think about examples, let's say you have operator that is better than trace class, so better than S1, then any M accretive, so anything that has numeric range on the right, would have complete system of projections because you have enough control of the resolvent norm. Meaning, to show completeness or to satisfy completeness is relatively easy. It's kind of mild condition. You need good resolvent behavior only in some parts of the complex plane, and in the other part of complex plane, it can be arbitrarily bad. So in the examples that I was showing in the beginning, like Davies oscillator, Bender oscillator, to show completeness with this theorem is 2 lines. It's really easy. Although the properties are bad, completeness is really easy, and it's easy to establish. Now, we are not really after the completeness. We would like to know more. We would like to see what is the condition on the perturbation under which we obtain the Riesz property of the projection. One of the classical statements from Cato tells us the following. If we start with self-adjoint non-negative operator with compact resolvent, simple eigenvalues, called μn, and 2 conditions are satisfied. The first one is that the gaps between eigenvalues, they grow, okay? So this would not be applicable in harmonic oscillator. First assumption is gaps grow. Second condition, perturbation is bounded. Then we get claims that we would like to have. Then for the perturb operator A plus B, eigenvalues are eventually simple. one has estimate on them, and most importantly, the system of spectral projections has the risk property. So this is one of the statements that tells you how much you can perturb, and still, even though the operator is not self-adjoint, it is close to self-adjoint. Now, the way how you can construct the spectral projections for this claim is that, let's say the eigenvalues of A of the unperturbed one are the blue balls here, and the perturbed ones are the red ones. The first projection is projection on multiple eigenvalues. There it's difficult to say what happens. Any kind of Jordan structure can appear there after perturbation, but what one can show is that it stops at some point. So you can include it into big rectangle or big box, and after that, all eigenvalues stay localized in balls around the unperturbed eigenvalues, and these balls do not touch. So you can nicely separate the spectrum, and based on this, you can also build the spectral projection. The first one, P naught, is always that one, the big that takes into account this finitely many. So there's some big matrix possibly with whatever Jordan structure you would like to have. But then one has only one-dimensional projections. So after that, everything is nice and simple. Okay, if I have this property, what does it tell me? Especially in the situation of this Cato's theorem. Well, if I have that, I can use these spectral projections, and I can simply decompose my operator to this big part related to this box, and then sum of restrictions of my operator on the invariant subspaces related to these simple eigenvalues. So my operator T actually has the representation as T naught, which is a finite rank operator, and then sum of projection with lambda multiplied by lambda k. Now, I know this is a real system, meaning I have this map that brings my projections to orthonormal projections. So if I apply this similarity transform, then on T naught, what I get is, well, this will be some finite rank operator plus orthogonal sum, and then this sum of orthogonal projection times lambda k. So this is actually diagonalization after this finite block. So in a way, what we obtain in this situation, that our operator T is similar to a sum of finite rank plus normal operator. And such operators obviously have very good properties, because all pathologies or defects that can appear are only due to the finite rank, which means matrix that we can control. We know, at least in principle, you know what is the size of that. So in particular, if I want to use these things for resolvent, it immediately follows that for a large lambda, the norm of the resolvent behaves as constant over distance of lambda to the spectrum of my operator. So in a way, this is the way how to find good operators. If you prove that the system of spectral projections has this property, then your operator has properties that are very close to self-adjoint or normal operators. Now, one, of course, can go further than Cato. I listed some of the references: Danforth, Schwarz, Marcus, Clark, Agranovich, Wyss, and others, where you always combine two ingredients. One is what is the character of the spectrum of the unperturbed operator. So this is the condition one. In Cato's case, it was the gaps are growing. Actually, one can be a bit more precise. One can allow different behaviors of gaps. They can go together. They can stay constant. They can get larger, and you can measure it by this parameter kappa. And then you can try to measure the strength of the perturbation in different ways. The classical ones would be this way, which is the relative boundedness, or this P subordination. And in the first example, which was the motivation for our research, there was a form version of this P subordination. All of that is nice. The problem is, if I go back to the two problems I mentioned in the beginning, so this was something like this: I want harmonic oscillator x to beta perturbed by odd imaginary function, or I want to perturb by delta potentials. None of these claims give you any result, or in the second one they give, but it's very limited. Clearly, you are not getting to the transition between good and bad behavior of the operator. And this was our motivation where to start. And this is what we got. This is one of the results in our paper. So if I again start similarly as Cato, non-negative self-adjoint operator with compact resolvent, simple eigenvalues mu n, and by psi n I will denote normalized eigenvectors of this self-adjoint operator. First condition, I measure the gaps between eigenvalues, so they should be like larger than n to kappa minus 1, kappa positive. So shrinking gaps are shrinking or constant gaps are possible here. And the second thing is, and that was the essential ingredient that helped us to progress, was the different way how to measure the size of perturbation. This then became known as a local form subordination, and it goes like this. You take your perturbation and you evaluate at the eigenvectors of the aperture operator. So what you are doing, you are checking the matrix elements of the perturbation, and what you want is certain decay, in this way multiplicative. If you have that, and if this parameter that measures the behavior of the matrix elements satisfies this condition to alpha plus kappa is larger than 1, then we get the claim S in Cato, for example. So eigenvalues of the perturb operator are eventually simple. One has a symptotic formula. Most importantly, spectral projections have the risk property, and the picture is similar. Again, we need to construct some projection of the low-lying eigenvalues. I can say how big is this and this rectangle, and then the rest stays isolated, and one has formulas for what happens with these red eigenvalues. Now, let me comment more on these assumptions. So we also know that we have this condition to alpha plus kappa is larger than 1. One cannot really improve in a way that if you allow 2 alpha plus kappa is equal 1, then the claims are no longer true. We have a counterexample for that. So from this point of view, it is sharp. Now, simple eigenvalues or non-negative operator, that can be relaxed, and we did not really do it in this form version, but in operator versions, these were done before. Analogous idea, but expressed in terms of operators, not as here this is convenient for forms, was there already before. This was first in the paper of Farushi and Mityagin and then Shkalikov. But let's say for very singular perturbations, operator version is not enough. So the form one was improvement, and the proof was very different comparing to the operator version. So this wasn't an obvious step. One has also survey of these results, and due to Shkalikov, and further improvements, and I would like to mention one of them in case of constant gaps. And the claims, and it's relatively new, are natural if you perturb by something which is less than half of the distance between the spectra, then still you get the claims or resistant projections. But what is really interesting in this paper is that the claims work not only for operators with compact resolvent. It can be separated blocks of general spectra, and you still get risk property of the projection. So this is kind of big step towards more general claims where you don't restrict yourself for eigenvalues only. Now, having this abstract theorem, I know which perturbations are maybe good. I can ask, okay, can I solve my original problem? I have a differential operator. Can I use it to say where is the transition? And this is what was a corollary of that result. If I perturb this Schrödinger operator with potential x to beta, let's say harmonic oscillator for beta equal 2, then if the perturbation can be written as a sum of these 4 things, then all the claims apply. So eigenvalues are eventually simple, and spectral projections have the risk property. What are these conditions? The first one is the pointwise bound on the potential. So if the potential does not grow faster than x to gamma, where gamma is restricted in this way, so depending on beta, I have now threshold for gamma. So this is the allowed growth at infinity, under which my operator is still good. Any LP perturbation in this case works also. So singular, not too singular, but L1 is okay, is there. One can even go to distributions up to certain order, and even things like infinite number of delta functions, if the couplings are reasonable here, L1, they still work. Now to get these kind of claims, and this is maybe the difficulty with this abstract criteria, this is not a trivial application of the theorem, because there the condition was take your perturbation, evaluate the eigenfunctions, and check the behavior. The problem is, for this kind of operators, eigenfunctions are not explicit. Maybe for harmonic oscillator they are, but anyway, you don't really care about the algebraic structure as exponential time Hermite polynomial. You need to know asymptotics. And not only pointwise, you need to know things like weighted LP norms of these eigenfunctions. So there is actually a lot of work between applying abstract theorem and getting to these claims, but many things are known and there are literature, so it could be used and it could be applied, and we got these claims. Now, I cannot say that if, and now I want to focus on this condition, if gamma is larger, then I don't have raised basis, because unfortunately there is not enough information on the spectrum of the perturbable operator, but there is strong indication that this condition is optimal, and I want to explain why.
So for beta equal to 3, this means that gamma is positive. Over there is negative.
It's negative. So good ones are if I have decaying perturbation.
So gamma equal to 1 is out of.
It's out of question. Now, so if I do not satisfy the opposite inequality, so what I showed before for gamma small, I have the real system of projections and I have good control of the resolvent. Resolvent behaves for large lambda as constant over distance to the spectrum. Now, what happens for gamma larger than b over 2, and this is coming from completely different work with David Krejcir, is that if I take my t and I check the norm of the resolvent on horizontal lines in C, so I go with real part to plus infinity, so I fix the imaginary part, this is the b, and I go with a to the right, so to the real part to plus infinity. Then for any n, the norm of the resolvent grows faster than a to the n, meaning that norm of the resolvent is really bad. It's, if I know where the spectrum is hard to imagine that this behavior of the resolvent norm would be due to spectrum. But since we don't know basically anything about the spectrum, especially multiplicities, I cannot exclude that this could be due to some very weird Jordan structure in the spectrum. I don't believe it is like that, but this is still open problem. But this is an indication that this condition is indeed optimal. Okay. Now I want to go back to here and go to the final part about the newest results. So I said this abstract theorem in a way was optimal because my condition 2 alpha plus kappa is larger than 1 cannot be taken to 2 alpha plus kappa is equal to 1. But there is one point that was bothering us all the time, who said that the eigenvalue gaps need to have this polynomial behavior or this power behavior. The same thing, why should I insist on here decay that is like power? How to get the claims where I can have whatever behavior of gaps, and here estimate with general sequences, and maybe I would like that some ability condition, and after that I get my claims.
Can you control actually the first assumption somehow in concrete situation?
Yes. So this, let's say for these ones, this is work of Titchmarsh for x2 beta. Yes, so these asymptotics are. So the question is, can we go to general behavior of the gaps, general behavior of matrix elements? What is the condition giving us the claims analogous to it? And this is what we did recently. So It is possible. It is the conditions are a bit more implicit, so that is maybe not that nice. But what was interesting for us is that the proof is new, and it simplified a lot. That we in the proofs that of the statements I showed before, it was really essential that the behavior was power-like. Now in the new work we could completely avoid that, which hopefully can open way to something new. So the statement is now a bit more complicated, but it's of the same type. I have non-positive self-adjoint operator resolvent in SP, normalized eigenvectors. Rn is simply the gap, size of the gap. And I assume that my perturbation now is subordinated in this way. I have multiplicative bound by a sequence omega j. Now the condition that guarantees that all the claims are true, so eigenvalues are eventually simple, and we have this property, is this. It is more implicit. One can see it as kind of transform of the sequence omega j square. So what do you do in position n? You just divide by the size of gap. In the other parts, you take the sum over j. J is not n, and downstairs is the difference. So these are omega, the distance between omega and omega j. Now, in case omega n omega j is, sorry, not omega, mu, the eigenvalues are like n. So downstairs n minus j. This is up to the absolute value. This is the Hilbert transform of the sequence omega j square. So in a way, for harmonic oscillator, this becomes object that is very natural in a way. And in other cases, this is something like generalization of discrete Hilbert transform, but with different behavior of the denominator. Of course, what is not that nice is this absolute value, because that makes problems. That makes the Hilbert transform, this modified Hilbert transform, much worse than Hilbert transform. But the point is that this is not unnatural object, although at the first sight it can look like that. Now, final comments, where does this appear? And this was also kind of satisfactory. We knew that this object is natural, but before we somehow could not make this machinery run under this condition. If you do the usual perturbation theory, so you write your perturb resolvent as this product, the term you need to control this one is the square root of resolvent, your perturbation square root of resolvent. And if you check Hilbert-Schmidt norm of that, you get this kind of sum, which is exactly then leading to those conditions. So what we are basically saying here, that if you have this multiplicative bound, then the only thing you need to know is that this term behaves well in sense it decays as slow as you want, as you go with z to infinity. Now, one can compare with the previous cases, and in those cases, when you have power-like situation, you can control these transforms. You can show that they have certain behavior. All formulas are here, so everything works. It's a generalization of what we did before, but now we can go further. So, for example, we can allow these omega j's instead of powers. They can be this log behavior. So much slower decay. It still works. Or, and this is maybe even more interesting, we can allow the cases where the bound on the perturbation on matrix elements is not regularly decaying. It is sequence of this type. So this omega n decays as slow as you want, but the sequence has a lot of gaps in sense that it is zero everywhere except when the index is the square of an integer. So this sequence, which has, if you think about support, the huge gaps and growing gaps in the support of the sequence, but the decay that we need is any, and it still works. So in a way, this was for us satisfactory that finally we could get to something a bit more exotic and get the proof that in a way is natural, that is basically using that the term that should be small, and after that everything should work, is enough. The control of this term is enough to conclude the good properties of the operator. So thank you for your attention. I will stop here.